Okay, so let's wait if anyone joins, then we will start again. Let's wait for 2 3 minutes. Okay, so let's begin. Okay. Hello everyone, my name is Raja Mukherjee and I am a research scholar at the Department of Computer Science and Engineering, IIT Kharagpur. I'll be taking this live session for NPTEL course on reinforcement learning. Uh, so, as always, we will be doing some tutorial for this week, that is week 10. We'll be solving some questions and answers, as well as I will do a quick recap of what was done this week. Yeah, can you hear me? Uh, could you please respond if you can hear me? Okay. Okay, so let's begin. Okay, so let's start for this week, that is week 10. So let's start the recap first. What was done? So, in last week, we came across functional functional approximation. So, of functional approximation of value function. So, so what was the reason we went for functional approximation of value functions? Right. Previously, we used to do a tabular kind of work. Right. Now, why we wanted to have a functional approximation for value functions? So the reason was very simple, that in a real world scenario, the number of states would be very large, right? So very large, like 10 to the power of uh, 25, like, like such big number of states can be there. Now, obviously, storing value for each of them, each of the states, action value pair for each of the states is very difficult. Storing is also, let's say, we have a good memory, we can store it, but the real bottleneck lies in the calculation of so many parameters. Calculation will take a lot of time. So instead, what we're trying to do is to find a functional approximation for these states, such that you you give him that, okay, this is the state. Give like you have a you will have something like a black box here. So where you will input state, and you will get the output something called f of s, which is basically a value function of s. So, right. So this was what we are trying to find out. So our goal was to find out this black box, so that acquiring that black box will give me a value function. So that was the reason for using functional approximation. So basically, task was to reduce the number of states. So this week also, uh, we were introduced to another such technique of reducing the number of states, which we called as hierarchical approximation, like hierarchical reinforcement learning. Give me a minute. Right. So, as the name suggests, our task is to divide the number of states, or the state space, into small modules or hierarchy. We have to set up a our main goal in this case is to set up a hierarchy or some kind of division in the states, such that we can reduce the state space. We don't have to calculate along so many, so like a big chunk of. We don't have to store a big chunk of state and action value pairs in our memory. So that is the reason we came across this thing called hierarchical reinforcement learning. It's quite similar. The reason to shift to hierarchical reinforcement learning is same, that we want to reduce our state space. Okay. So the concept is quite common, and which we have seen in other forms of programming. So other forms of programming, like in C programming, you have came across functions, right? So why do you use functions in a C program or a general programming language? To get some modularity. Yeah, the term is basically modularity, right? So you want to, so instead of writing the same code every time and again, what you can do is you can write, like you have to compute a factorial several times. Like you are writing a, suppose you are writing a code for a RSA, cryptography, code you are trying to make, and you have this thing called finding what is a whether a number is a prime number or not, right? you, you have to check it a lot of time. You have to check it in different parts of the code. Now it is, instead of writing the logic for is the code is a number is prime number or not, what you can do is you can write a small piece of function and you can write the logic there, and instead of writing the code each time, what you will do is calling the functions. So what specifically it gives us is modularity. Right. So you have a big task. You are dividing the task into small modules. Like let's say let's continue with the RSA algorithm. You have to implement an RSA algorithm. So you need a factorial function. You need a divide prime number function, right? So these things you can create a module and write it separately, which you can use not only for the RSA algorithm but for other future purposes also, right? So that's why it produces gives you a modularity, right? Now, how do you relate it to a how do you relate it to a reinforcement learning problem? How do you relate it to a reinforcement learning problem? So if your, let's say your task is to okay, let's use the same example which was given in the class. Let's suppose you are at room A. So suppose you are in this room and this is another room, right? And these are the two doors you have, right? So suppose you are here. Suppose you are currently here, and your task is to go. So this is room 2, and this is room 1. So your task is to suppose go here. So this is where this is where currently you are. Your task is to go here, right? So so what are the steps you will follow to reach that room 2? So obviously your first task will be get out of room 1, and the second task will be reach the destination in room 2, right? So these are your two tasks. So you can divide your task twice in two ways, right? So this is so the RL task is to go from one room to another. So you can just divide it up in two parts. That get out of room 1 and then you reach the destination in room 2, right? So that is a way you can divide your RL work, right? So nothing unnecessary here. It's quite easy to understand what we are trying to do here, right? Our goal is to reach that destination and room 2. So these are the two steps you need to find. Now these two are individual tasks, right? So get one out of room 1 and then reach the destination in room 2. These are two different individual tasks. So you can solve them individually and get a policy. So we can solve both tasks individually and get a policy, right? So we can do that. So that is the reason we call this uh, that provides a modularity in your um, hierarchy and reinforcement learning, right? So so one few questions. So let's clarify these questions. Number one, does optimal let's use a different naming convention. Does optimal task 1 and task 2 give us overall optimal solution? Number 2, does solving it together give a optimal solution, right? So you understand two questions, right? So does, suppose you are finding optimal solution for task 1 and similarly you find optimal solution separately for task 2, and you combine the policy and you say that okay, this is policy number 1. And the second approach is you think it as a whole as a single entity task, and you get a policy based policy, you design a policy out of it, optimal policy out of it. So which one will be more optimal, policy 1 or policy 2? So let me write it this one as P1 and P2, right? So true. When you are trying to find out, you are trying to think the whole MDP. So obviously, yeah, every reinforcement learning problem is a whole MDP. So you are trying to find out a whole MDP. So you are considering the whole MDP, the whole state space, and everything. So obviously, that will give you a more uh, optimal solution than giving than the. So again, it comes out to the local minimal maxima kind of approach, right? So you there is a pitfall that you get a base solution for task 1, but that solution and combining it with the solution of task 2 doesn't give you the optimal solution, rather it is a little suboptimal. But honestly speaking, that will be will it be very like, okay, I get it that policy 2 will be much better, more optimal solution, but isn't it more realistic to take the optimal solution of P1? So what advantage will P1 give me over P2? I get it, P2 will be much more optimal, but what advantage P1 will give me? Think when you have let's say 1,000, 10,000 policy, 10,000 states. Suppose you have 10,000 states, and instead of these two states, there are much more states. At that time, what will be which will be a more practical approach, policy 1 or policy 2? While policy 1, you take the optimal solutions for each submodules and then join it up. No, I'm telling you to find it, think about it realistically. Suppose you have a limited you have a limited resources in terms of memory and everything. So computing resources is, for you, is quite limited. Yeah, obviously. So that gives you the that give you the hunch, right, that solving those smaller tasks will always give you a better way to find out the, like, let's think about it. Like, suppose in for this 10,000 states you want to apply policy 2. So that may take you like to converge, let's say, it yields you a it takes you a very long time. So let's say 10 minutes, whereas solving those submodules and then combining it takes you around 4 minutes. So obviously you will always choose uh, one which, okay, it is not it is up to optimal, it is not fully optimal, but it is it gives you much more faster results. So in that case, obviously we will try to take this modular approach. So another feature of modular approach is, okay, it gives you a faster and no not it gives you a very faster and sophisticated result compared to a whole MTP problem. Another thing it gives you is the you can use the simply the modularity approach. Like in many cases, maybe that getting out of room one may be encountered in several solutions. Like, suppose there are many rooms, 10, 20 rooms, right? But getting out of room one is a common task in many cases. Like, there are 10 tasks are there. Like, this is going from one destination to another. There are 10 more destinations, like that, say. And this getting out of room one appears in 10 places, in the 10 tasks 6 times. So solving that modular solution, you only have to solve it once. You don't have to solve it all the times, all the 6 times. Only one time you get the optimal policy and use it for all the other 6 times, right? So you don't have to recompute it every time. You know, you know what is the optimal policy for this task, get out of the room one, and you always use it. So that's how less computation will also be required. So that there comes your modularity thing handy. Okay, I know what is the policy for this one. I will use it and simply leave the room. I don't have to think about, okay, what if I come from this state? What if I come from that state? And all. Right. So this modularity approach is clear, like what it serves and all. Okay. Now, there are three types of optimality in this hierarchical thing. So one is hierarchical optimality. Two is modular optimality. And three is flat optimality. So, uh, so let's come to all of it one by one. Okay. So again, let's use that get out of room study example. So you have a room. Room 2. Suppose you have to reach this destination. Room 1. This is your start state. Let's say that. So should I use something else that will also be great? Okay, fine. That is not a issue. This will be enough. So hierarchical optimality basically means there will be a hierarchy in the state space. There will be a preferable order in which you have to move to follow a policy. So what I mean to say is that, like in this case, you will be asked to say that to reach room 2 you have to come through room 1, right? There can be much more rooms. Like let me just give you another example. Let me read all this a little. Suppose this is room 3. Suppose this is room 3. So my so we can define a hierarchy like this. Hierarchy in the state space. So we can define a hierarchy like this. Uh, we can define that to reach destination you have to go from room 1 to 2, right? We specify a what about self-driving cars? What about self-driving cars? You can think this about a self-driving car.
Yeah, that's, I was trying to give you that example because instead of going from one room to another room, maybe we can think about the example of
Yeah,
self-driving.
you can simply think of it as a neighborhood. Like
Yeah, yeah,
you can think about it as a neighborhood, and you have a grid space like that. Basically, it is called a grid space. Okay, this walking or going from one room to another is basically a grid space problem. It Yeah. So what I was saying that suppose we define a hierarchy that we have to go from room 1 to 2. We define it that we have to go from room 1 to 2, and then we go to the destination, right? Right. That is defining a hierarchical optimality. So in that case, what will be the how are you going to define an optimal solution? So you have to think like this, that I have to go, not think like this. You have to, the problem statement becomes like this. So what will be the optimal policy such that I move from, mm what is the optimal policy to reach from start to end, provided that I have to move from room 1 to 2. So let me write it down. What is the optimal policy given we have to move from room 1 to 2, right? So that is how you are going to define your policy. This is and let's think about the modular approach. Let me define the modular approach also, the modular optimality. So the modular optimality guarantees individual module optimality. uh, Individual module optimality, right? So in that sense, what we will do is, uh, so we have already defined the task previously. So yeah, it will assume that going from room 1 to 2 is, you will find an optimal solution, and then you will try to find optimal solution from room 2 to the destination. Here is a major difference. Here arrives the major difference. So in this case, I have to think about that room 1 to 2 have to go, and based on that I will find the optimal policy. So the optimal policy can be something like this, right? And the second case, the optimal policy can be like this, the modular approach. So for the modular approach, the optimality can be something like this. Sorry, I did it completely different. Sorry. Yeah. So this will be the correct one. So for modular approach, hierarchical approach, this should be the output, right? Whereas for modular optimality, this should be the approach, right? I guess this is understandable, right? So in modular approach, your task is to find the optimal solution first to get out of room 2. So in that case, you will obviously choose that path. So so black is your modular approach. So black is your modular approach, and low is your hierarchical approach. Right. So the path may be same as well. I don't get it. The path may be same as well. Yes, the path may be same as well. Uh, yeah, the both path may be same as well, but it may also be different. But my understanding is, like, what I want you to understand is there is a difference for both the problem statement. The problem statement one hierarchy says that I have to reach from 1 to 2, and then I continue the optimal solution. So one task is given that I have to complete, and then the rest. Whereas in modular approach, my task is to find the optimal solution for each module. So for module 1, so that is, so the module 1, that is your get out of room 2, this is the shortest path, right? This is always going to be the shortest path. And then here to here you have to find that's their best policy which they have at that point. Yeah, so another thing may happen is that, suppose moving in this room, so in moving in, suppose room 1 is much more costly, maybe it is more costly than this moving in this room, right? So the rewards may be different. How to distinguish them? Why do you want to distinguish? right? You don't have to, you don't want to distinguish. Your task is to find one solution, which is cheap. No, you don't have, your task is not to find it uniquely. Your task is to find a solution. Like, so if you have done in your any machine learning problem and all, so when you are training a neural network, you have a constant. Your constant is your GPU. Suppose you don't have a very powerful GPU, right? Your what is your task? Your task is to find out the solution that is giving you a best accuracy. Think about it this way here. You have limited resources. You don't have infinite resources to find out, because always this will give you the best answer. So flat optimality is basically don't have to think about anything. So basically in flat optimality, what you take the entire state space and do your approaches for do your approaches for like those dynamic programming or TD0 approach, those, right, that will always give you the best solution. But what problem in that case is you don't have enough resources to carry out a TD0 or TD lambda, not TD lambda, TD0, or let's say your Monte Carlo algorithm, because that will cost you a very large fortune. So you are left with doing either of these two, hierarchical optimality or modular optimality. So you run modular optimality or hierarchical optimality. You check for your given resource and all, which one is giving you the best option, best result. So suppose let's suppose that modular and hierarchical optimality is taking the same amount of time for for this problem. So obviously in that case your choice will be to find out the one, take the one which will taking the least which is giving you the more reward, right? Basically the more optimal one. You don't have to think about identify the uniquely. It may not be unique. Let's say it gives you a suppose our start state is something different. So let's say our start state is something. Uh, let's say our start state is something here. In that case, it may be both will take the same or give you the same result. Maybe will give you the same results, both hierarchical and modular. So what could be a typical policy for getting out of room one? What could be a typical policy for getting out of room one? So you will basically take the door which is near, right? That is your basically the policy, the one door which is near. Okay, so that's a premiere on what is your hierarchical optimality and all, and what we are trying to do here. So any doubt you can ask. Next we will go to SMDP. Okay, so let's go to the next part. So now we will discuss the tools to how to find these hierarchical reinforcement learning solutions. What are the solutions there in the literature? So first, for going there, first I will discuss another important concept. So you have come across MDP previously. All these reinforcement learning problem are basically MDP. So what is your typical MDP look like? So you have a start state, you have a state, and based on an action AT, you get a reward RT and go to next state ST plus 1, right? Similarly, you take an action at plus 1, you get a reward rt plus, this is rt plus 1, rt plus 2, and you get a next state st plus 2, and then you continue. Right? This is your basically mtp. So what is the property of mtp? So mtp depends only on your action and current state and action, right? So that is what mtp depends on, right? So what similarly we have the concept of semi Markov decision problem, smdp. Similarly you have smdp. So what is smdp? So you have a state, you take an action based on the state, and wait for tau seconds, and you get a record rt plus tau, and you go to state st plus tau, right? And then you apply another action et plus tau, you get a reward rt plus tau das, and you go to stage st plus tau das. So the difference between mtp and smtp. So mtp assumes what does mtp assumes? So only the assumes sequential part of decision process is relevant, time spent is not. Whereas smtp assumes tau random variable is the time elapsed after taking action in state st to get to next state, right? These are all definitions. Right, this is basically a definition. So what was there in MDP, you don't care about how much time you have spent when you have taken from a current state, you have applied action and you go to the next state. You don't bother about how much time you have spent, but here you bother about nothing more. So this is basically a definition. Okay, so suppose you are now asked what would be the so all the other problems which you have solved here, like all the variables like from MDP you got the Bellman equations, right? So if you have to rewrite the whole ADL problem using SMDP, what you will do? So let's rewrite the Bellman equations. So what will be the Bellman equations for SMDP? So Bellman equations for SMDP will be, so it will be V pi of S max A belongs to A R of S comma A plus summation is dash tau P of gamma tau P of is bar comma tau given S comma A into V star of S dash. Right, this is your equation for your SMDP for your Bellman equation value function. So what was the for MDP, what was it? For MDP it was this. V star S is equals to max of A belongs to A R of S comma A plus gamma summation S dash P of S dash comma S comma A V star of S dash. Right. So see the difference. So you are adding this extra discount factor gamma, like not the extra discount factor, you have to include this extra random variable which you are using currently, that is tau. So also notice your transition is now different. So you are using both the variables S bar and tau, whereas previously you are using only S bar. Next state, not the you are only using the next state, not the tau variable. So what does this mean? So in a SMDP, the amount of time you have spent previously becomes a part of your value function. Your value function depends on it. So I guess the natural question will be why, right? Why do you need an SMDP? Uh, any suggestion? Why do you need an SMDP? Why we are discussing SMDP? Uh, why do you need an SMDP? So this should be a question to you, right? So you're why in the middle of everything we are discussing MDP previously, but why we are trying to now consider an SMDP? Why we are trying to use an SMDP? So let's no, no, no. You are stating a obvious answer that what is SMDP, right? So yours depends on time at which action is taken and all, but that is not it. So why we are discussing SMDP? So the natural answer is basically, let's come back to here. This is a whole other problem, right? Going from moving from starts to goal. So from this start state to goal state, from this state to this state is your RL problem, right? But we are trying to divide the whole, and that is your MDP. Remember that RL problem is basically defined by your MDP. But now what we are trying to do is we are trying to divide that MDP into smaller modules. Now here is the fun fact. What is the what is the like for those sub modules you don't have a end position, right? So that is your destination which you want to go, right? That there is no such thing, right? So your your option here was like your goal one was get out of room 2. So you can go it through here, from go it through here, right? There is no specific uh, place you want to go. You can go through anywhere. And are you going to how are you going to restrict, how are you going to divide it? The entire empty problem is there. You have to divide that state space, right? And the state space is trajectory. You have seen before, like it starts from a state and reaches a terminal state, right? So in the trajectory you are trying to divide the trajectory, right? So suppose this is a trajectory. So this is your trajectory simply. Let me just write it down. Suppose a0 sorry, suppose this is your trajectory: s0, s1, s3, s2, s5, s1, s3, and let's say s6 is your terminal space. Like this is your this is your trajectory, let's say. And what you are trying to do is here now, suppose you are trying to group, so there are 5 states: s0, s1, s2, s3, s4, and then you have s5 and s6. Suppose this is your one module and this is your one module, right? So how many times you are moving from one module to another here? So here is your one time you are accessing one module, then you are leaving the module, and then you are again going into the module, and then you are again going out to the second module. Oh, let me use a different color scheme. It will be a much easier to do. So this is one time you are inside module 1. So this is 1 and this is 2. Then you go to the module 2. Then again you come out of module 1, from module 2 to module 1, and then again you are going back to module 2. Right. So here you see you are going from one module to another and returning it and going out. Right? So now S6 is a terminal state, but here you see you are coming out from S2 and S3 for module 1. They are not your terminal state. So that's why when you are considering a sub problem like this, sub states like this, this is not an MDP, right? This is not an MDP. That's why you are using an SMDP. How many times spent, how much time has been applied and all. Okay, now you understood why you are trying to use an SMDP instead of an MDP. So any doubts regarding this, you can ask. Where is the modularity achieved? Yeah, I mean, this grouping is quite a modularity, right? So, these are two subtasks, right? These one and two are these are two subtasks, and you are trying to solve those subtasks. So consider that moving from one room to another problem, start to destination. Those are two substacks like that. That is the modularity achieved. Here also same. This grouping from one group to another. Maybe okay, maybe a toy example. But let's consider this is your this is your task of moving from room 1 to 2, and this is your task maybe of moving 1 to 3, something like that. Yeah, I mean think it like that way. I'm not giving a concrete example, but that is what I'm trying to express. Okay, so now we will look at two specific cases of like how to solve this hierarchical reinforcement problem, and two solutions to these problems. Okay, so one is your options. So one is your options. Okay, before that, let me just write these equations down. Uh, Q learning for MDP. What was the Q learning from MDP? Qk plus 1 s comma a is equal to Qk s comma a plus alpha r plus gamma max a dash belongs to a of s dash kq s dash comma a dash minus qk s comma a. Right. So this is your q learning from MDP. So similarly, what will be your q learning from SMDP? So what will be q learning from SMDP? So your q learning from SMDP will be q plus 1 s comma a is equal to qk s comma a plus alpha. So let me write it r bar plus gamma tau max of a dash belongs to a s dash qq s dash a dash minus qk s comma a, where r bar is equals to r t plus 1 plus gamma r t plus 2 plus gamma square r t plus 3 plus dot gamma tau minus 1 r t plus tau, right? So that is what your reward is. So notice this calculation of reward. We are taking into account, we are actually taking into account the time space between your the time you have taken an action and the time your action has you have reached the next state from s to s dash. So you take tau times that has been factored in, and that is your part of your equation. Okay, so this is by definition. How is it? Now let's come to options. So this is one way of solving your hierarchical reinforcement learning problem. So so this is basically a operator. Okay, so this is an operator. What you have here is three things. An option has three things: an I, a policy, and a terminating condition. So this is your I is basically your initial state, input set, so I is a subset of S, the total S space. This is your policy, and this is your termination condition. So so beta is some condition based on which your it comes out of a of a of a state. So suppose you are currently at state S and you take an action A. So it follows pi of s of A and goes to s dash. So where the option terminates by a function this. Okay. So what is basically an option doing? So this is a high level definition. Okay. So what basically is option doing? So option is again, as I told you, is a in your this example. This example. Let me rewrite this example. S0, S1, S4, S2, S0, S1, S4, S2, S5, S1, S3, S6, S5, S1, S3, S6. So your groupings are S0, S1, S2, S3, S4. Other grouping is S5 and S6. Right. So you will define one option for this, another option for this. Right. And I think it is quite understandable for you now right now. So this one is one group, this one is same another group, and this one is another, and this one is another. Right. Okay. So tell me, what will be the termination condition? What will be the termination condition for this? So what will be the termination condition for this? So if so, our termination condition for this will be beta S2 or beta S3, right? Because there it terminates from one option to another option, right? I hope this is clear for you. How we are trying to define your I, pi, and beta. So these are all your i's, right? These are all your subset of input set. Yes, this is i's, and this is your another input set, right? There is a specific policy we don't know. We know, but I haven't written any policy here. But there is some policy based on which this trajectory happens, and here is the reasons. You're only transmit like ending from state S2 or S3. So that is your terminating condition.
Sir, question S5 and S6 are also terminating condition, no?
Yeah, you have for that batch that option space S6, S5, and S6. That is your terminating condition. Okay, so this is how you define an option. Uh, obviously, what does the option achieve? Option achieves your modularity, your hierarchical modularity, or your simple modular optimality or hierarchical optimality. Both it satisfies. It may satisfy one of it each, but it depends. Okay, this is how you are defining your like options. So these are semi-Markovian options. Okay, so Markovian options and semi-Markovian option exist, but as the name suggests, what happens in case of a Markovian action? A Markovian action, you don't have the tau element. You don't have the option that there is a time element attached to it. But in Markovian option, semi-Markovian action, you have. So semi-Markovian means you have an history, like based on which you are terminating or not, right? So what? So as I have said before, as I have said before. So what is happening here? So we have an MDP. We have a big MDP. We are adding a set of options to it, and what you are getting out of it. So you have an MDP, big MDP, consist of all of it, and you're adding to it a set of options. What you are getting? You are getting a set of SMDPs, right? Right. That is what you are getting. You have an MDP. You are adding a set of options, and you are getting a set of SMDPs. And now, what you have to do? You have to find out the Q learning. So suppose you have done your options. Now you have to find out the action value pairs, and so that's why you have to do the Q learning. So let's do the Q learning for this. So what will be the Q learning for this options? So Q k plus 1 S of O is equals to Qk S comma O plus alpha R plus gamma tau max O0 O dash belong to O of S dash QQ QK S dash O dash minus QK S O. So that is your Q learning for this will be tau bar. So this is your updation rule, value function updation rule for what? For your options, for each options. So you are currently here and going to here, and for that you calculate these equations. So this is one option, and this is another option. This is your state space, and this I think you understand what we are trying to do, right? So uh, from what is the transition? Transition from one option to another option. Okay, so this is how you are defining the Q function for each options, for the entire sorry, not option, but for the entire for one option each for the entire MDP, right? Now, yeah, okay. Sorry, I'm back. My recording got little bit corrupted. Okay, so I have to do it again a few minutes later. But don't worry, now it is fine. So as I was just saying, so this intra-option learning basically takes care of these hops inside the transitions inside your of one option, and this part, this yellow part, that is what you are previously doing here, takes this jump from one option to another. Uh, is this part clear? Like I hope this one is very easy to understand. Not much tough thing there. So if you have any doubt, you can ask. I was little bit. So if you have any doubt, you can ask regarding this.
So it's just this equation Q learning
Mm-hmm.
still that applies to SMDP, right? Not in
Yeah,
SMDP.
this is completely SMTP, right?
Okay, because you're changing state, like go from one object, like
This is an SMDP, but what previously you need to understand is that here we are using this R bar because we are not considering these hops inside it. What we are trying to do is we are trying to just calculate uh, using this formula a rough estimation of what is the reward inside it, right? This part we are calculating and substituting it here, but here it is not the case. We are counting the hops we are making inside the option, so that's why you don't have to consider the tau, but it is part of an SMDP. So if you are adding this RT plus 1 and all, you will again get that tau value back. Okay, so let's go to the next one. The last hierarchical approach that was discussed. It is called, HAM, hierarchies of abstract machines. So as the name suggests, there is a hierarchy of. So we what we have in this case is that we have a set of machines, right? So so a set of machines like HI, okay, and each machine state machines, basically state machines, okay. So each machines have four states: action, call, choice, and stop. Okay, these are the four states you have. So you have a given MDB problem. What you have to do is you have to divide that MDB problem into various machines. So let's use an example first to generate it. So let's say the uh, okay, let's discuss few points before. So one point is how action is generated. So action is generated based on your MDP policy, uh, MDP state. So there is an MDP. Your MDP state ST, as well as your current machine state MPI. MTI, current machine state, and st is your current MDP state. Okay. Other things that we need to discuss is, okay. So there is always a start start main machine called ham, which initiates the call, which initiates the MTP, right? So now let's get to the example and get these things cleared. Let me just delete one. Okay, so suppose we have an MTP of a robot. Suppose we have a robot uh, which, suppose we have a grid like this. You have a grid like this. You have a robot here which starts and it stops when it reaches an intersection. Suppose here is one intersection and here is one intersection. It stops when it reaches some intersection. Okay, and let's say its state transition diagram is something like this. Start. So it follow a wall. If there is an intersection, it stops. If there is an obstacle, so suppose here it reaches it, there is an obstacle, it enters the choice state. And another option is back off, like it goes beyond the obstacle, right? So something like this. So here it makes one call as intersection and another is obstacle, same. Okay, so now let's define all three of the states which we first said ham has: action, choice, call, and stop. Okay, so what does stop happens? When does stop happen? So let's not consider stop first. So you have a let's say a robot, and this is your let's say this is your initial ham machine. So this is your ham machine, like initial machine. Initial machine. So it start with the follow all. Okay. So what is a follow all? So follow all. So initial machine, right? Follow all. One machine, and similarly back off. Back off another machine, right? So there are three machines. You have ham, you have a fall off, and back off. Okay. So what does ham do? So initially when you start it, ham calls this. Ham calls this follow off, follow all by default. So this is one machine. Uh, Follow all one machine, ham one machine. It calls follow all. Okay, directly calls follow all this machine. So what will follow all do? Follow all will have its own state transition diagram that is beyond my scope. No, I will not think about it. But suppose it reaches an instruction, it has follow all will also have these all states. Okay, action, choice, call, and so on. But when follow all reaches an intersection, what happens? A stop happens. So what happens when it reaches an intersection? It stops. So what does it do? It makes a it terminates that machine and returns the control back to ham. Okay, that is what your follower does. Suppose what it gets a obstruction. It gets an obstruction. The follower gets an obstruction. So what it will do? It will go to its choice state. So choice state will make a choice whether it will follow the wall or it will back off. Okay, so it will go to the choice state. Choice state, there is some policy. So the main RL part, so RL is basically a policy, is defined in this choice state. So there are four states. Okay, call, stop, interrupts it. Choice determines this which state to go. Okay, so if it says that no, you have found an obstruction, so this may be an obstruction. Okay, you now follow the wall, or you can back off. Right? These are the two things you can happen. So this choice, this RL part that is there in the choice, it determines it, and then it makes another call. What is the call? If the choice determines that it will follow all, it will call a follow all function, follow all state call, follow all machine. Else it will call a back off machine. Right? It may also choose to terminate, but I'm not saying that it will not terminate, but it may choose that. So that is how your hierarchical abstract machine works. So it basically a set of machines and it have a state of states. Now you will ask, what does action come in? So I have called about choice. To call choice is basically making the choice which transition to make. Call calls that machine, and stop terminates a machine. But what does action do? What does action do? Action basically generates the state from the MDP. So if you are in a follow all state, so currently you are in some MDP, you are in currently in some state. Okay, suppose you are here, and your ham is currently at follow all machine. Follow all, uh, follow all machine. Okay, so it takes this thing, it takes these two and generates an action. What the action can be for the robot? That move 4 steps forward, move at an angle of 45 degree, move at an angle of 90 degree, right? So that is the action that it generates when you take this MDP and the state of the machine it is currently executing. It takes that into account and generates an action, right? That is your concept of hierarchical abstract machines. So any doubt regarding this, you can ask. I know it is a little confusing. These calling of so one way you can think about this calling of machines as your when you are calling a nested function one after another, you make a stack like this. So similarly, there will be a stack like this here. So any doubt you can ask now regarding this. So the RL part lies here in the choice state, because there you have to select categorically which option, uh, which state machine to select. So any doubt you can ask. I know this is a
So
very
the sorry, so the Q learning equation will still be the, what is it?
yeah,
This.
Q learning equation will surely be there, but it will be in the this choice section. So there is the Q learning equations I have, but I don't want to go into that complexity. But those Q learning equations will also be here, but it is a little bit complicated.
Oh,
So you can so you know the text from where we are referring to this. So in that research paper it is there. Uh,
okay.
so
Yeah. Yes.
I will share the link. Okay, 1 minute.
I know this. I mean, don't waste time. Yeah, it's there in the,
It's there, right?
yeah, yeah. It is there in the Excel sheet, right?
I don't think so. I don't remember it is there in the Excel sheet. But okay, I will give it to you one hour only. Yes. Yeah, this is the paper. You can find the equation here. Okay, so let's go to solving the problems which we have this week. Okay, question one. Suppose that in solving a problem, we make use of a state distribution, state abstraction, identifying solution to some problem problems. Is it in this approach it is possible to obtain a recursively optimal solution to the original problem? Think about it and say the answer. So what it says is that we use a state of abstraction identifying solutions to some sub problems. Okay, so you have some sub problems to a whole MDP problem. So what you are saying is that you are recursively finding the optimal solutions to these sub problems. You are finding the optimal solution to these sub problems. Is it possible to find optimal solution to this sub problem? Like if you combine this result, combine the results, can you get a uh, optimal sub solution? Can you get an optimal solution compared to the MTP? Yes, the answer is yes. So I'm not satisfied with the individual yes thing. What what basically they mean, what basically this question means, if suppose you are adding up all this one, can you achieve a optimal solution to the original problem? Answer is yes, because depends. Yeah, depends. Yeah, true. It depends. But you can get. It is not impossible that okay that the suboptimal solutions the recursive the modular solutions doesn't add up to the optimal solution. It is not that impossible. Sometimes it is possible. Like it is not something called like not impossible completely. It is possible. Okay. So let's go to the next one. Recursive formation equals certain extra things to consider. Yeah, true. It can be considered. What I'm trying to say is that suppose this P1 optimal plus P2 optimal plus P3 optimal plus say P4 optimal is let's say equals to P. What that was thing they want to ask, that is it possible to get? I mean, the thing is, it may be possible, but it is not always possible. But it is possible to get an optimal solution like this. Suppose the optimal solution for P is exactly what this policy which we derive by adding up this. It is not something impossible. It is possible. It is not that completely impossible. Let's say 10% of the time, if you are lucky, you get a optimal solution based out of it. Okay, so let's go to the next one. What kind of solution would you expect to obtain if, in solving a problem, policies for each individual subproblem are learned in isolation? So, what kind of problem we are solving? If let's say, again, let's consider this is your MDP, and these are your problem P1, P2, P3, P4, P5. It's saying that we are individually computing these optimal solutions for each of them. We're individually calculating P pi 1, P star pi 1, P star pi 2, P star pi 3, P3, pi, pi star P4, and pi star P5. Okay, and mm, we are doing it in isolation. Huh? Why flat optimal? What is flat optimal? Flat optimal is solving the MDP. Flat optimal is solving the MDP. What we are trying to do is the sub problems we are trying to solve, and in isolation. There is no relation between. It thinks that there is no relation between P1, P2, P3, and P4 and P5. So it will be recursive solution, right? Because there is no relation between P1, P2, P3, P4. What if it is hierarchical? What it would happen? That it would said that P2 given P1, this kind of relation would have been there, right? Right. This is understandable, right? Why it is recursive? Do the policies of individual options need to be defined over the entire state space of MDP? So what it is saying is there is one option, there is another option, there is another option. So suppose this is pi 1, pi 2, and pi 3. So it is saying, do the policies of individual options need to be defined over the entire state space of the MDP problem? Yes or no? So the answer is no. So because uh, each of them we are considering, there is a for yeah, sorry again, my recording got stopped. Yeah, as I was saying that that options are helping you to do a subset of the states, so you don't have to think about it. Okay, so let's go to the next one. My recording is a little bit causing an issue. I will try to wrap it up quickly. Okay, so consider two room example. Suppose you define two options, uh, O1 to take an agent in room 1 to room 2, and O2 to take the agent from room 2 to goal state. Assuming that you have an appropriately selected the initiation states and the termination condition options for both the options, and are trying to learn the individual options policy, would you need to use a SMTP Q learning or conventional Q learning? So it is saying that consider two rooms example. uh, okay, the first part is correct. So suppose so suppose you define two options, O1 to take the agent in room 1 to room 2, and O2 to take the agent in room 2 to the goal state, assuming that you have appropriately specified the initiation states and the termination condition for both the options, and are trying to line the individual option policies. So you are trying to find out the individual options policy. Okay, would you need to use a SMTP Q learning or a conventional Q learning will suffice? So what it is saying is that you are making a the transitions inside the option, and you want to learn the policy regarding it. You want to run a policy regarding it. So which options will you select? Yeah, correct. Inside the one, you can use a conventional Q learning to do it. You don't need a SMTP Q learning, because you are not uh, you are considering it as a subspace. You are trying to find out the option in it. You don't have to use SMTP Q learning in that. SMTP Q learning you will require when you are making the jump from one option to another. That time you are going to require it. Okay, so let's go to the next one. So suppose consider a Markov policy over this Markov policy, given a Markov policy like this, S comma O to Z, where S is the set of states and O is the options. Assume that the options are Markov, while the policy selects options by considering the primitive actions being selected in those options. We can determine another policy pi which corresponds to u, but is a conventional policy of election. Will pi be a Markov policy? So it says that policy u selects options by considering the primitive actions being selected in those options. Okay, so policy u selects options, so you have a policy which selects which options to pick and okay. In the option we can determine another policy pi which corresponds to u but is a conventional policy over all action, but is a conventional MDP policy. In general, will pi be a Markov policy? What it will be? So you have a policy pi which selects options. So this is an option, this is an option, this is an option. You have a policy pi which options to select for which state, right? And you have another option, policy pi. So also this policy is Markovian. So this selection of, it is not a SMDP Markov we are considering. We are considering a Q is a mu is a Markov policy. Selection of just mu. So while mu selects the options, we cannot determine another policy pi which corresponds to mu but is a conventional policy over all actions. So you have a mu which considerable policy over all actions. Will pi be a Markov policy? Will pi be a Markov policy? So the answer is no. So in such an option-based thing, when we have such an option, so how are you going to select the pi? Pi will pi will be selected not only action will be selected not only on the state but also the option being forwarded, right? So as a result, whenever you are considering the option in such a case, it means it is associated with the history. So the answer will be no in such a case. Okay, so let's like I have three more questions. Let's wrap it up quickly. Okay, so consider the problem design problem. Following problem design, you have a grid world with several rooms. Several rooms are decided with a goal state in a corner cell of one of the rooms. You set up an agent with options for existing one of the rooms to another. You allow the agent to pick up 4 primitive actions. The step reward of -1. The algorithm used is SMDP Q learning with normal Q learning updates for primitive actions. You accept the agent to learn faster due to the presence of the options but discover that it is not the case. Can you explain why? So you are using options but you find learning is slow. They are asking you why. The options are not useful for solving the problem, hence slow down. Initially, the agent will focus more on primitive action, causing slowdown. Due to the presence of options, we can no longer achieve optimal solutions, hence it is taking longer. No, that is absolutely wrong. It takes longer because you are using an SMTP Q learning compared to a combination learning. That is not also the case. So, what will happen? So one of the reason is that the agent is actually focusing more on the primitive action. So the actions uh, inside the options, that's where you are trying to spend more of the time. So that's the reason it is causing a slowdown. Okay, so let's go to the next one. So using intra-option techniques, you can learn about option even without executing them. So this one is true because if you come back to here, this equation, you see you are considering all the states here that are not only in the options, but whenever you are making a transition from the next option, you are considering it also. You are considering all the states. Okay, so this one is true. And the last one is, suppose you have identified a set of subtracts for solving a large problem using hierarchical machine learning. To solve such subtract efficiently, you want to constrain the primitive action that will be executed distance. So specifying such constraint is possible in, so this is possible in both of them. That constraint, you want to constrain the primitive action that can be executed using subtracts. So it is possible in both ham and options, simply by limiting the policy. Like you have to give the policy, right? It has to be I, pi, and beta. So you can limit it in options to do it, and similarly in ham also you can do it. Okay, so that was the last slide and the last question. So we will again meet next week. Thank you for joining. Yeah, thank you. Yeah.